introduction. It's very good to be here with all of you. And then, I have prepared actually for 3 hours, but there is a very important lecture from which you will benefit much more than benefiting from my talk. So we decided that all of you should attend that talk. That's on weather radars, perhaps. Weather radars, vision and rainfall. So definitely we will be more enthused by that talk listening to me. So I think I will compress it in 1.5 hours now. By around 3:30 we will disperse. Because I need to compress, perhaps I had 2 options. One is to cover one topic to the depth, or another is to give a broad overview of several issues that we discuss in water resources, hydrology, vis-a-vis. So I have adopted the latter path to give you a flavor of several aspects that we deal with, several processes, and the way we generally model, and how we use these hydrologic models in the climate change impacts. So please do not expect any in-depth coverage of any particular topic. But if you have any questions, please feel free to ask, either now or even after asking. So essentially, we will be talking about hydrological processes. Now, for most of you, hydrology may be new, the word itself may be new. The job of the hydrologist starts once the rainfall reaches the ground. So all of this, these days we have been talking about how the rain clouds are formed, how rainfall occurs, what kind of different types of rainfalls and so on. So you are all always in the atmosphere. Now we start coming to the ground. What happens to the rainfall is within the purview of the hydrologists. So we will start looking at how the rainfall converts itself into various processes such as soil moisture, evapotranspiration, infiltration, interception, etc., which all have implications on the water availability for the human consumption as well as the water demands and so on, as we will see. So what happens to the rain is the question that we will be addressing. So this is the way I will organize the lecture. Essentially, I will introduce the hydrologic cycle, how the water vapor moves in this universe, and then focus on certain processes of interest to hydrologists, namely interception, the infiltration, evapotranspiration, runoff, and so on, and just give you an idea of how these are estimated for hydrologic processes. Then I will introduce you a few hydrologic models, 2 hydrologic models, which we use typically in the climate change impact assessment. And then answer the question specifically on how the water resources are likely to change over the coming decades. So, if you are looking at streams, rivers, or lakes, or anywhere you see water on the ground or below it, you should think that it is a hydrologic problem. So we will be interested in answering questions such as how the stream flows are likely to vary over the next about 30 years, 40 years, not because of the climate change. Or how the evapotranspiration from the vegetation is likely to change because of climate change. So these are the questions that we will address. And I will introduce the methodology by which we address this. Specifically for looking at stream flows. If you are not used to the word stream flow, look at large rivers like Brahmaputra, Divecha, Krishna, Contd, Mahanadi. These are the rivers that essentially give us water. Because most of the water comes from these rivers. So a question that is relevant to be addressed at this point in time is that given the climate change is occurring, given that the temperatures are changing, the sea levels are decreasing, and precipitation patterns are getting affected, given that these things are known to be happening, how is the hydrology of these river basins likely to change? In as much as the water availability is affected, the water usage demands are affected, water quality is affected, the floods and droughts are affected, and so on. So these are the questions that we will try to address towards the end of it. Now, because the time is short, what I will do is be about first 45 minutes I will cover the basics of the hydrologic processes. Next 45 minutes I will talk on the climate change impacts. So hydrologic cycle, you can start either from the left end or the right end. What we are interested in is Once the precipitation falls, it may be stored either in ice or snow, in the glaciers or in the ice that is on the surface. And part of it also falls on the, in fact, majority of it falls on the land. The precipitation that falls on the land may convert itself into surface runoff, that is running off on the surface. But part of it also goes as infiltration into the ground. You imagine there is a sand surface or sand layer and you put some sprinkles of water. Bulk of it just flows down into the sand. So it goes as infiltration into the ground. The infiltration that goes into the ground may in fact add to the groundwater storage. There is a deep groundwater aquifer or groundwater storage that is available. So the infiltration can go and add to that. Alternatively, it can also go horizontally in the ground, which is what we call as interflow or subsurface flow. So it can go as subsurface flow until it hits a water body, like a lake or something, or it can directly go into the ocean. The groundwater itself is always in a flux. Remember, groundwater is not stationary, it will be always in a flux because of hydraulic gradients. So it is moving, and then the groundwater itself may hit a water body such as a river or a lake, and then it contributes as what we call as base flow to the streams. So wherever there is a groundwater interception that happens, can we take out this or because this part of the figure in fact, this is where the ocean lies, right? I don't want to see the rather than the ocean. So this surface water, for example, we were talking about the groundwater here. The groundwater flow may intersect with the surface water flow, and then it contributes to the surface. Imagine that there is a river that is going, and then there is an aquifer that comes and joins the river. Then the groundwater can be actually contributing to the stream flow. Remember, in rivers like Ganga, Brahmaputra, Krishna, etc., which are perennial rivers, that means even when there is no rainfall, you see flow there. Why does this flow occur? It is essentially because of groundwater contribution. Groundwater flow is very slow, so there is a time lag between the contribution of the groundwater and the precipitation process. So this is what we call as base flow. Base flow is the contribution of the groundwater to the stream. Similarly, the groundwater may actually intercept the ocean itself. Look at coastal regions, for example, look at Chennai, Bombay, Gujarat, Surat, and so on, which are coastal regions. There is a coastal aquifer, and that will be actually intercepting the ocean. So the groundwater will also contribute to the ocean. And there is a interplay between the coastal water and the groundwater in terms of the mixing of the flow. The coastal water or the sea water has a higher salinity compared to the groundwater, which is the fresh water, and therefore there is a mixing that takes place up to a certain point. And that's why some of you may be aware of salinity intrusions into the groundwater in the coastal regions. If you dig a borewell very close to the ocean, you get saline water. And we will see the implications of climate change on this first of all. So we took this. Look at the other. From the ocean, all of this part will be knowing much more than me. Evaporation occurs, and then condensation, and then precipitation can occur on the ocean itself, or the moisture will move over land and then precipitation will occur. Now, what happens to the water bodies? There may be natural lakes like this, or there may be artificial lakes. For example, you may have created a dam here, and because of which there is a lake or a river. From the reservoir, there is an evaporation that takes place. There is also an infiltration happening here. For example, here the infiltration takes place. And you have freshwater storage. On the vegetation, you have evapotranspiration taking place. From the base surface land, there is also evaporation. Now, as you can see, the water is in a continuous flux, continuous movement. In one form or the other, it is continuously moving. And this movement is what we need to capture. So when we are looking at hydraulic processes, water is never stable. Water is in continuous flux. And we may be interested in certain aspects of the hydrological cycle and we focus only on the hydrological cycle. Alright, now let us look at the same thing, you just understand it this way. There is a precipitation that occurs. Precipitation may be rainfall or snowfall and all forms of precipitation. At the first level, there will be interception because you see a thick forest, let's say. On the thick forest, there is a rainfall occurring, and rainfall is only drizzle, very small rainfall. What happens? Bulk of the water is intercepted by the leaves and other surfaces of the forest. It never reaches the ground. So interception is the first thing that happens. The second one is that as it flows, as it reaches the ground and starts flowing on the ground, there will be a lot of natural depressions. And it has to fill up those natural depressions before it will get water to the stream. So these are the first level processes that occur. Then there will be infiltration, water goes down, and apart from all of these, the overland flow occurs. It means when all of these are satisfied, then the overland flow starts happening. That means the water will now start flowing on the surface. Now each of these will have their own processes associated. Interception is on the, typically on the vegetation, leaves, etc. The water falls and the leaves captured. So if you have a very thick forest, bulk of it will be captured by the leaves and so on. So eventually what happens, the water will evaporate from that and then it is lost to the flows. Similarly, from depression storage, there will be evaporation or evapotranspiration. By evapotranspiration, I mean base surface evaporation as well as transpiration that is occurring from the vegetation. Both together we call it as evapotranspiration. Then, as I said, from infiltration, part of it can go as interflow or subsurface flow, and part of it can go as groundwater recharge. That's the ectophyte. And some of it can go as deep flow. What I mean by that is that the recharge is taking place on the water surface, groundwater surface. But eventually it can go into deeper storage. So it can add deep groundwater storage. From the interflow, it can go into channel output. Aquifer recharge, it can go into channel, as I showed here. Then from the overland flow also it goes to channel. By channel input, I mean there are natural channels, natural streams, and the flow that occurs on the surface will eventually join these streams. That's a channel. And finally, it converts itself into a stream flow, which is the output. So from precipitation, it has gone through several processes before it reaches the stream flow. So if you plot the stream flow here as discharge versus type, this is how it goes. So this is the direct runoff. As the precipitation falls, it goes through several processes, and then as a runoff, it finally adds to the stream flow. This is called as a direct runoff. And then you also have the route of groundwater flow, that is the base flow. So the stream flow will consist of direct runoff as well as base flow. Now we look at the interception as the first process that occurs. As the rain falls, it is intercepted not only by the vegetation. In the case of urbanized areas and so on, there you have lot of built-up areas. So if the rain falls, the roofs will capture the rainfall. So there is an interception of the rainfall that occurs before it reaches the ground because of vegetation as well as the rooftops. Eventually, this may evaporate. Bulk of it may evaporate. Or if you are talking about interception by vegetation, after some time, it may just fall on the ground. If it falls on the ground, the loss that is happening because of the vegetation is returned to the atmosphere by evaporation. Then we call it as interception loss. That means it is not available for runoff, it just goes off. Whereas the other two types of interception, we call it as through fall. After some time from the leaf, it may directly go down, or it may just take its own time. These are important because of the lag times that we talk about in the rainfall, in the runoff. It may just follow the stems and think that you look at very tall trees. It may take some time and then reach the ground. Then we call it as stem flow. So the first process that we talk about is the interception. You look at some thick trees like this, beech tree and so. You imagine if the rainfall intensity is very small, it is just happening at a very low intensity rainfall, and then there is a very thick forest. Then the interception will be large. The percentage of rainfall that is retained as interception is very large. But as the rainfall intensity increases, what happens is bulk of it starts coming down. Therefore, the infiltration rate starts coming down. So this is what is shown here. You can quantify this. So at very low rainfall intensities, the infiltration interception is very large, and then it reaches a certain threshold value, and then it gets. However, it is very difficult to measure the interception because it changes from one place to another place. So we generally use these kind of empirical relationships based on the type of vegetation you have, based on the type of built-up area you have, and so on, and then model this interception process into the hydrologic model. For example, we take something like this. Let's say you look at the interception loss. You may have the interception storage. This depends on the type of vegetation, the type of built-up area, and so on. Then you may have a ratio of vegetation surface area to its projected area. That means you have a surface area, you project it from roof to X day, you get some area there. And you also have rate of evaporation, is the rate of evaporation. And this is the time of duration of rainfall after the rainfall has started. So this is how we estimate, and I repeat that these are mostly empirical type of relationships that we use for interception. Typically, about 20 to 25% of the rainfall. If you have very thick forests and the rainfall intensities are low, about 20 to 25% of rainfall will be lost as interception. Then if you look at surfaces like this, the rain is falling and then there are surfaces like this. So this has to fill up all the voids and the depressions. This is called as the depression storage. After the interception, the next important loss that takes place is the depression storage. Now this will depend on the type of soil, the type of surface that you have, and so on. So you can imagine that if it is a completely a desert area and the water just descends, bulk of it will go down into infiltration and depression storage. So this depression storage is eventually lost to runoff because bulk of it goes as infiltration, and if you are storing it for some time, it also goes as evaporation. So this is also taken as the initial loss. That means from the rainfall, interception has occurred and then the depression storage has occurred. These constitute the initial loss. This is what we mean by depression storage. The land surface is never smooth. There are always some depressions here. So first it has to fill up the depression, and over and above the depressions that you have, these are natural depressions like this. Over and above that, it will start drying off and then eventually reach the stream level. Now, for the depression storage, as I said, it depends on the type of soil, it depends on the condition of the surface, amount and nature of the depression, then the slope of the catchment itself. You imagine if you have a very mild slope and compare that with extremely steep slope. In a mild slope, the storage will be more because it doesn't run off easily. Whereas in the steep slope, the water will be running off faster. Again, for depression storage, it is extremely site dependent, and therefore we will not have expressions. That is, physical models are not possible. So typically, what we do is we develop empirical relationships for the depression storage, much as we do for interception, and then we have an important process of infiltration. As the precipitation occurs here, you imagine this is the soil, the top layer of the soil. Let us say that the rainfall has occurred over the last about 5 days, and already the soil is saturated with moisture, then any amount of rainfall that you provide, moisture that you provide, it cannot absorb. So that becomes runoff later. Soil can absorb water only up to certain capacity. If you take, let's say, 6 centimeters of soil on the ground, it can absorb water only up to certain capacity. That's the saturation moisture content. Once the soil reaches the saturation, then it can no longer absorb the moisture. And therefore, it depends on the antecedent conditions of the soil. How saturated is the soil before the rainfall actually occurs. That's the antecedent. And then we can go as recharge to the water table, this is water table. By water table, I mean the surface of the groundwater, and you will also have a temperature slightly above it, depending on the type of pressures that you have. Now, infiltration, luckily, is more amenable to analytical solutions. And therefore, we have mathematical expressions. Anything funny here? I'm asking you. Okay. I understand after 2 o'clock it is very difficult to sit in the theory classes like this. And in fact, if you ask me to sit, I'll be dozing off regularly. But unfortunately, you have to go through this. Let's go through it for another 45 minutes. Now, the infiltration is the process of water penetrating from the ground surface into the soil, as I have been saying. Now, we have an infiltration rate. You imagine the soil is completely dry, and then there is a rate of runoff, rate of rainfall that is happening. If the soil is completely dry and the rate of rainfall is small, what happens? All of it goes down. That means the capacity of the soil to absorb water is still there, so it keeps on infiltrating. As the rainfall intensity keeps increasing, a situation comes where the rainfall can balance reaches and equilibrium reaches, where only part of the rainfall goes as infiltration, the remaining part goes as runoff. So this is what we mean as infiltration rate, is the rate at which water enters the soil. Then we have some usual normal equations that we use, water equations, phase equation, Green-Hand method, etc. These are derived based on physical laws. The Richards equation is the one that governs the infiltration process, and these are all derived based on the Richards equation. So look at a small, simple experimental setup here. Let's say you have a wire mesh, and then you put the wire mesh on the container, small container, and the container already has a certain amount of water, and then you start sprinkling water onto that. What happens? The water starts going down into the container. Therefore, whatever you are inputting, whatever you are sprinkling, will go into the container. However, as the container starts getting filled up, it comes into this point. Then what happens? Any amount of water that you put will simply spill out. So there are two aspects here. One is that wire mesh that you consider is an indicator of the capacity to let the water in. If the wire mesh is very big, then whatever water you pour on it, it will go down. But if the wire mesh is very thin, there are lots of boundaries and so on, it is blocked and so on, what happens is bulk of the water will not go through. So there are two conditions. One is how porous is the soil medium to absorb the water. The second one is the container capacity is here. It can hold water only up to a certain point, and therefore the soil moisture can raise only up to a point where the soil gets saturated. Up to saturation, it can hold water. Beyond that, it cannot hold water. So this is the principle by which we model the interception. So this is intensity of rainfall. Intensity of rainfall, I mean, it is depth per unit time. Typically millimeters per hour, millimeters per second, and so on. So we are talking about depth per unit time. Similarly, the capacity that I talked about just now. Imagine the capacity of the soil to be field capacity, let's say. That means you can fill up up to that point. If you pour any more water, it either goes down or goes up as runoff and evaporation and so on. So field capacity is the final capacity of the soil. So you have the infiltration capacity here. If your rainfall intensity is greater than the infiltration capacity, it can go only as much as the capacity itself. Wire mesh can hold only certain amount of water, can pass through only certain amount of water. When the intensity is smaller, then it will equal to the intensity. Whatever you are pouring goes down. So this we model using what we call as the Hamiltonian relationship. So you imagine a dry soil, completely dry conditions, summer conditions. Last 5-6 days there are not rain at all, high temperatures, that the soil conditions are all extremely dry. Then slowly the rainfall starts occurring. As the rainfall starts occurring, what happens? The infiltration keeps picking up. And then if the rainfall continues for a longer duration, the soil moisture becomes higher and higher and it reaches the field capacity, after which it remains constant. So this is what is indicated here. At the beginning of the storm means a particular rainfall event. The rainfall starts and continuously rains for certain duration. That duration is called the storm duration. Now, as you can see, infiltration capacity, if you look at, first of all, it doesn't depend on the characteristic of the soil. Loose, permeable, sandy soil. Again, you have to relate it with that wire mesh example that I gave. If you make the wire mesh very big, that means the grain size is very big, then most of the water goes down. Similarly, you take sandy soils, they are all very loose, lots of pores are there. So whatever water you put in will go as infiltration. Whereas you take clay soil with no pores at all, then the infiltration capacity will be small. Then you have surface of entry, surface covered with grass or vegetation. What it does, grass or vegetation, if you have, generally loses the soil surrounding to it, and therefore the infiltration capacity will be more. Bulk of it goes as infiltration. Then fluid characteristics, turbidity of water, temperature of water, and all of this. So what we generally do is that this is the rainfall. The bar charts provide the rainfall. We put a cutoff based on the infiltration capacity of the soil, and this is the model that we use as Horton's model. This Horton's model is simply a mathematical equation. K is a constant here, P is time, and then F0 and Fc are the infiltration rates. Fc is the capacity, which is the constant equilibrium rate that occurs at the end of the time, and this gives you an exponential curve. Anything below this is the infiltration. Anything above that becomes the surface runoff. When you do the actual measurement, this comes very close to this idealized curve. If you do actual measurements, it becomes a figures up to this point. There are certain errors associated with it, but for all practical purposes, this is a good approximation of the infiltration curve. Then we look at the most important aspect of the evapotranspiration. Remember, we are talking about partitioning of the rainfall into various processes. We looked at the interception, that is the infiltration, and we looked at the depression storage. The most important hydrology process is the evapotranspiration, because we are talking about large expanses of land where there will be vegetation, natural vegetation in terms of forests and so on. There will be also crop lands, agricultural lands and so on. So there is a huge extent of vegetation that is present. And therefore, we need to look at evapotranspiration. It is very difficult for us to segregate base surface evaporation and the transpiration. And therefore, we use both these terms together and call it as evapotranspiration. Although, for agricultural experiments, it is possible for you to actually segregate how much is the transpiration. But for hydrologic purposes, the transpiration amount is very small compared to the base land evaporation, and therefore we combine these two terms and talk about evapotranspiration. So the evapotranspiration will consist of evaporation from the land surface and transpiration from the vegetation. Together we call it as evapotranspiration. Now let us say that there is a vegetation type and the soil moisture is not in deficit. That means you are able to supply the water that is required by the plant. The rate at which evapotranspiration occurs when there is no deficit of soil moisture is called as the potential evapotranspiration. So potential evapotranspiration is only measured with respect to moisture only. When there is no deficit of soil moisture, there is adequate moisture available, then the evapotranspiration that occurs is the potential evapotranspiration. However, as the soil moisture starts depleting, you imagine there is a crop or there is a tree like this, a large tree, and then it is able to absorb water at a certain rate. Now, this rate of absorption of water by the plant will depend on what we call as soil moisture stresses. Now, the soil moisture stress will depend on the actual soil moisture available. If the soil moisture is at field capacity, that's a complete capacity is filled up with soil moisture, then it will be at the potential evapotranspiration. The rate will be at the potential rate. As the soil moisture starts going down, the soil moisture stress increases, and therefore the evapotranspiration will be at lower rate compared to the potential evapotranspiration rate. So if you are interested in crop growth, then you need to maintain the evapotranspiration at near potential evapotranspiration rates. So it also depends on the vapor pressure. For example, this is you have the saturation vapor pressure and the actual vapor pressure. This is a constant. So it just depends on the difference between these two. And naturally, it also depends on the temperature. As more energy, the evaporation rates will be more. Now, all of these become important when we look at the climate change issues, because as you know, all of these aspects will be affected by climate change, and we need to look at these factors. Now, wind, you look at the wind. Let's say you have vegetation, and then you are looking at the evapotranspiration in the vegetated area. There is a vast expanse. Why does evapotranspiration occur? It is because of the gradient in the moisture content. Now, if there is a wind that removes all the moisture just surrounding the vegetation, then the gradient increases, and therefore the evapotranspiration increases. However, this can occur only at a certain point. Let's say you have such large winds that they have removed all the moisture already. Then any further increase in wind will not increase the evapotranspiration. So this is what we talk about, is the effect of wind. Similarly, atmospheric pressure will be decreasing barometric pressure in higher altitudes. That increases evaporation. Then it also depends on soluble salts, heat storage of water. For example, you play huge lakes with large depths of water. They have heat content. They store the heat in the depths. So compared to shallow water, the deep storage is similar to oceans, and you would have learned in other courses. They store heat, and they may release heat during the winter time, and therefore the evaporation may actually be more during the winter time on the surfaces of these lakes and other things. Now, there are several ways of estimating evapotranspiration. There are very vigorous analytical and physically based models. We will just introduce one, but you must remember that evapotranspiration can be actually estimated very accurately compared to most other processes in hydrology. And evapotranspiration is in fact the most important hydrological variable when we talk about climate change. So in the energy balance method, we simply look at how much is the energy that is coming in on a particular control surface, how much is lost everywhere, and how much is consumed by vaporization. That's all that we look at, and then look at how much is the volume that actually comes as the evaporation. So if you look at, now there is no time to go into all the derivations. So if you look at a control surface like this, you may have sensible heat to air. The net radiation is what you are getting here. And this is the vapor flow rate, this is the density, this is the area, and this is the evaporation. And similarly, you have what was the water level at this point. This is the rho A, air density. And there is also a heat conducted to the ground, heat loss to the ground. Now, we go through some rigorous derivation, and finally arrive at this. This is the evaporation rate, this is the net radiation, this is the latent heat of evaporation, and this is the density of water. This is after you inject this sensible heat as well as heat to the ground. These are negligible when you are comparing large surfaces. So you ignore the heat loss to the ground as well as the sensible heat loss to the surface. And for all practical purposes, remember we are talking about large river basins here. So the evapotranspiration, we are not talking at the lab scales and so on where these terms will become important. But we are talking about large expanses where the other terms will be much more important. For example, the net radiation is the most governing factor in our case. So let's look at it just to get the feel for these numbers that we are using. Net radiation may be of the order of 200 to 150 watts per meter square, and then depending on the temperature, etc., you can get the LV, that is the latent heat of vaporization. And we will use some road of view and look at the type of numbers that we get. So first we get the LV, is a latent heat. Now this is the heat that is required in joules for 1 kg of water to vaporize at 100 degrees centigrade. Now for temperatures you put this correction in degrees centigrade, and then you get this as joules per kg as the latent heat of vaporization. And if you use the road of view at 997, you get 7.10 meters. You can verify that the units are in meters per second you get here. Because kg per meter cube and draw nothing cancel, and finally you get 8.22 into 10 to the power minus 8 meters per second, which will be 7.10 meters per day. Now these are the types of numbers that you should get used to. Typically we are talking about 10 millimeters per day, 15 millimeters per day, 7 millimeters per day, etc. So this is the kind of evaporation that occurs. We call it as evapotranspiration in this case. The last important hydrology process that we talk about is the stream flow. From the rainfall, we looked at the interception and penetration storage and the infiltration that goes into the ground and the evapotranspiration that goes out. Now the remaining part is simply the stream flow. It has to come up on the ground and then flow over the surface of the ground. So large proportion of the precipitation contributes to surface storage, infiltration, etc. Now, let's say again, look at that example where your soil is completely dry and the rainfall starts occurring. You will not see any surface runoff at all. The water will not come on the surface because the bulk of it has to go down. As the intensity starts picking up, the soil moisture capacity is reached. It cannot infiltrate at a rate greater than the rainfall intensity, and therefore the difference between the rainfall intensity and the rate at which it can go down, that starts coming out as runoff. This is called as Hortonian overland flow. That means the soil moisture gets saturated, and because of this soil moisture getting saturated, the water cannot infiltrate any further, and therefore it starts coming out as overland flow. This is the Hortonian saturated runoff. There is also another type of runoff that takes place. The soil moisture is saturated not because of the precipitation that comes from above, but it comes from below. Let's say that there are valleys or the groundwater level comes up, and therefore it gets saturated from below. And then also the runoff occurs for a given precipitation, and that is called as non-Hortonian flow. Let us say you look at the stream flow. That means what we are looking at is that after the runoff starts, there is percolation. Percolation is the same as infiltration, and then there is an interflow. As I said, this is subsurface flow and infiltration. There may be a case where all of these will be simultaneously occurring, and the moisture that we are supplying may be contributing to all of these. And then the surface soil here gets saturated, and then this comes as surface runoff. And there is also a base flow that contributes to the stream flow. So the stream flow now consists of two major components. One is the runoff that is occurring on the overland. This is called as the overland flow. And another is the groundwater contribution, which is called as the base flow. Together, it is called as the stream flow. The stream flow is contributed by both of these. Pardon? Percolation is the infiltration that finally adds to the groundwater. There is a certain difference, but we can use them in analysis. That means infiltration can also go as horizontal flow as interflow, but below the interflow it percolates and adds to the ground. So we distinguish slightly between Hortonian overland flow and saturated overland flow. As I said, Hortonian overland flow occurs because of precipitation saturating the soil from above, and the saturated overland flow is actually saturated from below. Finally, when you are looking at the stream flows, you must remember that in terms of water availability, in terms of anything to do with water, the stream flows are the most important variables. They indicate the water availability in a river basin. You must be aware now that there are conflicts of Krishna waters to be shared between 2-3 states. Narmada waters being shared between Madhya Pradesh, Gujarat, Rajasthan and Maharashtra. And now there is also a conflict between Karnataka and Tamil Nadu for Kaveri water. All of these will depend on the stream flows. And therefore, getting the stream flows accurately is the single most important aspect of hydrology. Stream flows can be measured very accurately. They can also be estimated reasonably accurately if you know the processes, the other processes. For example, from the precipitation, how much went as losses and how much is remaining as balance. You account for all depression, storage, etc. in percentages, and then you can estimate stream flow at a particular location reasonably accurately. What we then use is that for a given precipitation, let's say the rainfall starts today and continues for 3 days without interruption. Now this is called as the storm duration. That means the storm has started today and next 3 days it has gone. Typically they may last for 6 hours, 8 hours and so on. During the flooding season, as it happened in Bombay in 2005, continuously for 5 days it rained. Or 3 or 4 days it rained at very high intensity, intensities. So this is part of the storm duration. And at a particular location, we are looking at the flow that is occurring at that location in the basin. We talk about a basin like this. This will be generally a deep structure. There will be channels, natural channels, and precipitation is occurring all through this area. And this precipitation, after satisfying the depression, storage, etc., runs on the ground and joins these small streams. All the small streams join the bigger stream, and then we will be looking at what is the response of this stream to this particular pattern of rainfall at a particular location. And this is what we capture through the hydrographs. So hydrographs are the important tools that we use to analyze the stream. It simply indicates for a given storm, it indicates the flow versus time. So this is the rainfall that has started. Initially, you will have base flow contribution here. This is the base flow, that is the groundwater. So the flow there was slowly reducing when the rainfall was not there. And then the rainfall starts and then the stream flow starts. Imagine rainfall starts occurring at uniform rate all through. What happens? This rainfall has to convert itself and come here first, and then flow through this channel, join a bigger channel, and then reach this point. So there is a time lag from the time the rainfall started to the time it reaches this point. There is a time lag. As time progresses, therefore, this stream flow here will keep on increasing because more and more area starts contributing to this. And that is why you get the shape like this. The stream flow will start increasing and then it reaches a particular point where the rainfall stops. Now the rainfall stops. At that point, the entire catchment would be contributing to that, so it reached a peak value. And then once the rainfall stops, it starts going up, the flow starts going up. So that is why typically we get this kind of shape. It is possible that the rainfall may continue for longer period. It does not mean that it is equal to keep on increasing, because you imagine that this is the basin and you are looking at the stream flow at this particular location. Rainfall occurred, let's say, for the first 3 hours. In the first 3 hours, this entire catchment starts contributing to this point. No matter how much time the rainfall continues, as long as the intensity remains the same, this flow will remain the same. It will continue for a longer duration, but it will not increase further, as long as the rainfall intensity is uniform. And therefore, this peak may continue for a long time, and then once the rainfall stops, what happens then? Let's say suddenly the rainfall stops all, then slowly it starts withdrawing. That means first these portions will stop contributing, then these portions will stop contributing, and so on. Because the water is still flowing into this, and therefore there is a delay before the flow stops, between the rainfall stopping and the flow stopping. And that is what we get in the hydrologics. Let's say, like I said, in the perennial rivers, you don't have any rainfall at all. After monsoon period, there is absolutely no rainfall. But the groundwater in alluvial rivers, where it happens, there is a groundwater storage, and groundwater releases water slowly, at a very slow rate, it will continuously release the water. And that is the base flow water. So when you see perennial rivers, during the non-monsoon, non-rainy days, the water that you are seeing there is because of the base flow, groundwater. So these are the processes that we are interested in now. Again, just to quickly recapitulate: precipitation, interception, infiltration, evapotranspiration, and the stream. These are the primary processes that we are interested in. Interception and the depression storage is very difficult to analytically arrive at expressions. Therefore, we use mostly some empirical relationships. Whereas for any other variable that we talk about in hydrology, we can bring out physical values. We use what are called as the distributed models. You will look at this particular catchment, this part of the catchment or watershed. Now, on this, the soil type will be varying all across. The vegetation type will be varying. This may be completely forested area, this may be completely urbanized area, this may be cropped area, and so on. So the vegetation type is changing, soil types are changing, the weather may be changing, the climate may be changing all across. And therefore, all these processes that we talk about need to be addressed at small scales. So we look at what are called as the distributed hydrologic models. We have grid size much similar to your climate models or land surface or models, ocean models perhaps that you are used to. We analyze these on grid sizes. And from one grid point to another grid point, we bring down the processes. At each of these grid points, you may simulate all these processes. For example, streamflow, evapotranspiration, soil moisture, evaporation, all of these processes that we talked about. We simulate that for a given input. Input is primarily the precipitation, but you can also have other variables. For example, temperature, relative humidity, etc., which drive evapotranspiration and other processes. From one element to another element, we keep routing these. We satisfy the continuity as well as the movement of equations when we are looking at the flows across the grid points. And then bring it down to the basin outlet. For example, here, we bring it down to this point. In doing so, we are not just looking at the surface of the basin, but also we go down and look at the soil layers. Typically, you may have agricultural area here, and you may have soil layers like this. So we go down and then simulate the soil moisture also. So soil moisture will give you the response in terms of the evapotranspiration for that particular vegetation. So all these processes are simulated at very small grid points, and then we connect these grid points from one point to another point. Typically, we talk about sizes of 2 kilometers by 2 kilometers, 5 kilometers by 5 kilometers. For large basins. And therefore, when we are looking at climate change impacts and we want to couple these hydrologic models with the climate models, we need output side those small grids of 2 kilometers, 5 kilometers, and so on. Because all these hydrologic processes occur essentially at small scales. And it is very difficult to generalize these hydrologic processes at large scales. Yeah. Yeah, we use satellite. I'm just demonstrating that. That's a good point. Most of the data that we need, apart from the local data, for example, precipitation, the type of vegetation, etc., that you need to get from the local. Even the vegetation and land cover we get from the satellite measurements. We use those. So I will just demonstrate two major models, which are both freely downloadable from the web. The first one is called the HEC HMS. That is, we have what is called a Hydrologic Engineering Center of the US. HMS is the Hydrological Modeling System. This can be downloaded. You simply Google HEC HMS, you can download it. And it is a very comprehensive hydrologic model, which is developed by an Army Corps of Engineers. HEC is part of the Army Corps of Engineers. And it simulates as dendritic watershed systems. By dendritic, I mean it divides it into small watersheds, and each of these watersheds it simulates all the processes. Not in the grid size that I mentioned. So it has what are called as sub-basins. So the entire watershed is subdivided into several sub-basins and then it simulates. These are some of the details you can go through. I leave the PPT here. Typically what it does is that all the processes that we talked about, from the precipitation you come to the land surface, and depending on the type of vegetation, type of the soil, type of the characteristics in terms of the slope and things like that, it simulates the land surface and generates overlap. Similarly, it simulates the infiltration depending on the soil type. Part of it goes as the interflow or the subsurface flow, and it can add stream. Then it also has an aquifer model, groundwater, and then it connects into the stream. So all the major processes are separated, and finally what we are interested in is the discharge, the river flow at a particular location.
So,
yeah.
Can we able to do rainfall runoff coefficient in this database?
Rainfall runoff coefficient. If you are talking about that rational type of formula, runoff equal to CIA, and you are talking about the sea, that doesn't need this model. It requires the catchment characteristics essentially. For example, in a campus like IISc, if you want to get sea at various locations, you have to look at what type of vegetation, what type of land cover, etc., and then you can estimate sea. That is the empirical relationship. Whereas this is the physically driven model. You can put that information externally into these models if you have another runoff coefficients. And then, finally, it just calculates based on some simple mass balance. This is the precipitation, this is the actual evapotranspiration, this is the infiltration, and this is the base flow. Now, there are various ways in which it can compute. The formula that we used earlier, several of these formulas are used, several of these models, and it estimates the runoff at this location. Now, these are some of the details, how to set up the basic model, and so on. I'll explain this through an example that may become easier. So as I said, these hydraulic models, we need to establish at large river basin scales or watershed scales or stream scales and so on. So if you look at one of the case study, this is Tungabhadra basin in Karnataka, Tungabhadra River is there. For this Tungabhadra basin, let us try to set up the HEC HMS model and see what type of data is necessary, how do we optimize the parameters that are there, and so on. Now this is the study area here in the Karnataka state. The catchment scale is of this order, 15,000 square kilometers that we are taking here. Now this soil data, as someone asked, the soil data, land use data, etc., these can be obtained from the satellites. There are global data sets available. From the global data sets for your platforms, you can specify the platforms, you can get all the soil data. Once you get the type of soil, you can get the soil properties. For example, we could estimate that part of it is clay loam, part of it is clay, sandy clay, etc. Once you get these, then you will use the speedometer type of functions and then get the parameters of hydraulic conductivity, field capacity, and so on. So Similarly, from this is obtained from the soil map, satellite maps, you get the land use and land cover. So this is the type of land use. Now this will be necessary because depending on the land use type, the type of evapotranspiration that comes out is different. So you have a soil map, you have a land use vegetation type of map, and these have to go as inputs into the model. These are some of the details here. These are not from satellite images. Then you also have, for example, these hydraulic conductivity, maximum moisture density, impervious percentage, basin land, etc. There are some guidelines available based on the type of land use you have, based on the type of vegetation you have, etc. These guidelines are available in the HEC HMS manual for different climatic zones, different land use patterns. You can get these things. Now, this will give you some idea. Remember, basin land means what I just indicated there. Your hydrograph reaches a particular point and then remain constant there. The time that it takes from the beginning of the storm to that point where the entire catchment is contributing to that particular point in the stream flow. That's part of the basin lag. So the basin has a certain amount of time lag between the rainfall occurring at the farthest point. From this farthest point, it has to reach this point. Now, obviously, it will depend on what is the catchment flow, what is the vegetation, what kind of resistance it has on the way, and what kind of soil properties it has, so that as it is running off, it will infiltrate and so on. So this is what is the basin lag. Yeah, and typically these are the line lags.
Basin lag is equal to time of concentration.
It is for all practical purposes, but there is a small difference in the time of concentration and basin lag. If you look at the hydrograph, anyway, I think it is too much of a detail. For the time when you take it as time of concentration, there is a very subtle difference between time of concentration and basin lag. Time of concentration is when the entire catchment is contributing. Basin lag may be slightly different from that in terms of the actual peak flow occurring at that particular location. Because of several reasons. Let's not worry about it. Time of concentration is equal to basin lag as far as our models are concerned. Now, this is the type of basin lags that we get, 3,800 units and so on. When we are talking about the small sub-basins like this, these are the types of areas we are talking about. Then you also need the climate data, hydrologic data, and so on. Remember here, you would have at a particular location like this, you would have the historical data, let's say last 30 years to observe the stream flows. These are important for us to calibrate and validate the model. Because now we have set up the model and it is generating the stream flow at that location. We want to be sure that the stream flow that it generates are in fact representative of that particular model. Which means we should validate this model with respect to the observed data. Because there are a large number of parameters which need to be calibrated at that. And for this, we take we subdivided into 4 sub-basins. Typically, this sub-division of basins will depend on the land use as well as the catchment characteristics and so on. So there are guidelines available in by which you can subdivide these. And this is the precipitation for which we'll run the model. At various locations, you have the observed precipitation data. And then you run the model on a daily scale by putting actual precipitation at these locations. For example, Harihar, Ravalakwadi, these are the stations where the observed precipitation is there. You pick up that observed precipitation, run the hydrologic model, and generate the output. Similarly, you have observed flows. This is a flow time series for the same period. And you have a way by which you can extract the base flow. You have extracted the base flow, and because you need to calibrate the model with respect to not just the stream flow, because you must remember that the hydrologic models, as indeed any other model, may work well for wrong basins, and you have to be alert to that. If you are looking only at the stream flows and calibrate all your parameters, you are able to generate the stream flows correctly, but your evapotranspiration may go haywire, base flow may go haywire. And therefore, it is important for you to address the calibration and validation with respect to as many variables as possible, and you optimize your parameters with respect to those. These are some of the other parameters that we use: initial depth rate, maximum depth rate. So initially we have initial estimates of these parameters. We go into the model with these parameters, and then in the calibration we optimize these parameters. And finally we get the output. There is a big story there. We are not going to all this. Simply understand that there is a model available to you. There are a set of inputs which can be obtained from satellite images, from the observed data, and from other estimates, etc. You run the model, calibrate it with respect to the output that you have observed output, and once you are satisfied for the calibration period, let's say you have 50 years data. Use about 30 to 40 years of data, first 40 years of data to calibrate the model. What do I mean by calibration? Is that you get the output as close to the observed output as possible for that period. Then for the remaining 20 years, you validate the model. That means you simply run the model and then compare it with respect to how it performs. This may happen, you are going to do it iteratively. For the climate change studies, we have a very important model, very useful model. This is called the variable infiltration capacity model. Remember here, in the HEC HMS, what we did was that we subdivided this watershed into several sub-watersheds, and then simulated this watershed separately, this watershed separately, and so on. But the land surface is so heterogeneous, and the vegetation and the land use patterns are so heterogeneous that even within the sub-basins, the infiltration capacities may be changing. All the characteristics may be changing at very small scales, and that the HEC HMS cannot capture. Therefore, we need to go at much smaller scales. And typically, for using climate change impact studies, we need gridded models. The HEC HMS or the SWAT, soil and water analysis tool, they are not grid-based models. They are based on HRUs, for example, SWAT, hydrologic response units, and here it is based on sub-watershed. So we need the gridded models, and WIC is a gridded model. The major advantage of WIC is that the grid size here can be as low as about 12 kilometers per kilometer. And typically this is what we need in hydrology. In fact, we need much smaller, but 12 kilometers is acceptable. 180. At each of these grid points, it simulates all the processes. For a given precipitation input, it simulates evapotranspiration, canopy evapotranspiration item, and it has typically 3 soil layers below the canopy. And you have the subsurface flow, gravity flows, how much flows into the different soil zones, and so on. So the WIC simulates rigorously all these processes at a grid point. And these grid sizes can be adjusted between 180 degree to about 1 to 1.5. I think about 1 degree. You can go up to 1 degree. And this again, we have done it for upper basin. Typically, what we do is this 1 degree by 1 degree precipitation that is available. So the input is available at 1 degree, and therefore set up the WIC model also at 1 degree for this entire basin. And these are the meteorologic variables such as precipitation, maximum temperature, minimum temperature, wind speed, etc. These are actually measured values. The wind speed is given by the Princeton University database. So as I said, there are many global databases available for running most of the hydraulic models. You can look up those global databases and then use it. Then you also have soil data. These soil data are also available from these soil maps are also available from the Princeton University site here. And you put the soil map onto the basin map, and these are the parameters. For example, B may indicate infiltration zone parameter. Then you have maximum velocity of base flow. Then you have this is not something like the initial value of 0.001. So there are also guidelines on what type of initial values you can use, and what are the range of these values. So what we do is similar to what we did in HEC HMS. You start with the initial values and then run the model, look at the output, and then adjust the model. Typically, these parameters, there are several of these parameters. In fact, in the big model, we go up to about 14 or 15 major parameters that we need to treat. But you can do some sensitivity analysis to begin with and identify those few parameters, let's say 3 or 4 parameters, which are for which the model output is extremely sensitive, and then just concentrate on these 3 or 4 parameters. And then optimize these parameters such that you get the output to the extent desired. So here we do B, DS, and WS. B regulates the infiltration as you saw, and DS regulates the base flow, and WS regulates soil moisture storage. In an iterative way, we do the validation of the model. Like I said, first you calibrate with respect to the historical data, part of it, and then the remaining part you use it for validation and so on. Similarly, you need the vegetation library. This is just to give you an idea of how detailed it goes into these models. So you have all of these models. LAI comes as one of the model parameter variable, albedo comes as one of the variable, and so on. So there are 13 variables for vegetation. Then you have vegetation parameters. It is graded in a different file, number of vegetation types, and so on. Remember, these are minor level details, but largely you must remember that we started subwatershed in the HEC HMS, and in the SWAT we do HRUs, hydrologic response units. These are very large scale processes still, and therefore we need to bring it down to smaller scales. And in the big, what it does is the subgrid variation of the soil type as well as the vegetation type is taken into account. That's why it's called as variable infiltration. Even within the grid, the infiltration capacity can vary. So you can specify your land use and the soil variation within the grid. In that. Although the final simulation is not done at the grid scale. And typically you get outputs like this. So in the calibration you look at how well it has performed with respect to the historical data. There are any number of measures by which you can check whether the model performance has been satisfactory. Typically use R-square value or RMS value or NASA's Sutcliffe coefficient and so on. There are many number of variables where measures that are available to check the parameter. So in summary then, so far we have seen the hydrologic processes and how we use the understanding of the hydrologic processes into hydrologic models. Typically we use distributed or semi-distributed. Incidentally, the HEC HMS model that I showed was a semi-distributed model. It is not completely distributed. Similarly, big model is also semi-distributed in the sense that for that grid size, it is in the grid size of one, let's say 12 km by 12 km, the process is all lumped. Therefore, it is also a semi-distributed model. In truly distributed model, what happens is that all the processes as they actually happen at the point scale are simulated. So these are all semi-distributed models. So we know now how to simulate these hydrologic processes through semi-distributed and distributed models. Now we look at the climate change implications, how we assess the climate change impacts using all these models. I will just rush through this because I have only 20 more minutes. Essentially, you must understand that for hydrology, you have evapotranspiration as one of the major variables, you have runoff as one of the major variables, and precipitation as one of the variables. Evapotranspiration is affected by all of these, all of which are likely to be impacted by climate change. I hope you had one lecture at least on climate conditions. So, when your temperature changes, evapotranspiration changes. When your relative humidity changes, wind speed changes, vapor pressure changes, etc. So, all of these will be impacting directly the evapotranspiration. Similarly, you look at the runoff. Apart from all these land use characteristics, for example, if the rainfall occurs on a catchment like this, immediately it gets converted into runoff. Whereas here, as I said, there is a sluggish response of this catchment, because there is an infiltration that takes place, in interception that takes place, and so on. The runoff that you get will be slower and it will also be smaller runoff. So, apart from the physical characteristics, it will also depend on a lot of meteorology and climate characteristics, antecedent function and rainfall duration, distribution of rainfall, etc., which are all likely to be affected by climate change. And we are looking at systems like this where we have created a reservoir and then the river flows like this. You are using the water for various purposes and there is a groundwater aquifer here that will be contributing as waste flow, and these discharges are the pollutants. For example, you may have industrial discharges, municipal discharges, then the precipitation that occurs on the agricultural land and converts itself into overland flow on the agricultural land will become pesticides, fertilizers, etc., and add to the pollution. And this is a continuous or uniform pollution that comes to the flow. So, in the context of climate change, we need to ask several questions. As the temperature changes, as the precipitation patterns change, how the flows are likely to change, how the quality is likely to get affected, how the frequency of floods and droughts are likely to change, and how the water demands in terms of the evapotranspiration are likely to change, and so on. Now, when we do this, we have to form recourse to the global climate models or the general circulation models. These are the most credible tools that are available today for projecting the climate change into the future. The point that you must understand is, standing at this point in time, we are going to make estimates about how the water situation is likely to evolve over the next 20 years, 40 years, and so on. Now, for this, we fall recourse to the global climate models. These operate on large grid sizes, typically of order of 2.5 degrees, and even the rest of the models that are available today, maybe of order of 140 degrees, and so on. And the variables that are of interest to hydrology, namely the precipitation, the evapotranspiration, soil moisture, etc., these are not well simulated by the global climate models. What they do simulate well are the temperature, pressures at different heights, and so on. So there are two major problems in using the global climate models directly for hydrologic impacts. One is the scales, spatial scales at which they operate. The other one is the variables of interest. Now these two problems we address through what is called as a downscaling. In the downscaling, we bring down large-scale outputs of the climate models to hydrologic scales. That's the first thing. Second thing is, we also relate the variables of interest. Let's say I'm interested in precipitation at a particular location, but this precipitation is not well simulated by the global climate models as a variable. However, it simulates well the humidity, the wind speed, the temperature, etc., which will all affect the precipitation. So we will formulate relationships between precipitation, for example, with those variables which are well simulated by the climate models, or these relationships sacrosanct for the future, and then use the climate models to predict the precipitation. That's the whole idea. Why do we hold? How can we hold these relationships into the future? The idea there is that your processes may be changing, your variables values are changing, but the governing relationship, governing physical relationship, the way precipitation is formed, or the way runoff is formed, the physical processes, they will not change. Only your inputs to those processes are changing. So that is what justifies the holding of these relationships into the future. So this is what we call as downscaling. Now these are the global climate models, and these are the typical grid sizes. The grid sizes vary from one location to another location, and so on. So we bring it down to the scale of interest in hydrology. And there are extraneous inputs available. So from the global climate models, we pick up the simulation for the next century, let's say, between 2000 to 2100, or 2020 to 2100, we pick up the simulation for any climate model. And then there are also extraneous inputs of topography, and cover, and so on. We bring all of these into hydrologic model and run the hydrologic model and simulate for the future how the streamflow is likely to change, how the evapotranspiration is likely to change. So we formulate the possible future hydrologic scenarios based on the climate scenarios. And these climate models are run for several scenarios as well. Typically, I will run through some examples fast. You look at the precipitation in the Odisha meteorological cycle. This is one precipitation value, and you have DCM grid parts here. We use what are called as the predictors and predictors. So the variable of interest is called as the predictor. So we want to predict the precipitation here into the future, for which we use different climate predictors that are provided by the DCMs at these grid points. Now these can be mean sea level pressure, sea surface temperature, and so on, which are well simulated by climate models. So initially we use mean sea level pressure and geopotential height at as predictors. There is one more issue. One is that you need to develop these models based on the historical observed data. But for most of the climate models, climate variables like this, which we use as predictors, there is no historical observed data. And that is when we use what is called as the reanalysis data. So typically, NCEP and CAR gives the reanalysis data. I think in other lectures you would have heard about this. Typically, they use all the available data sets, including the satellite measurements, the point measurements, etc., and then they interpolate this all across the globe. So, at scales of 2.5 degree by 2.5 degree, typically you get all these variables, sea level pressure, geopotential height, for the previous year. You use those and develop the statistical result. What I mean by that is that you have precipitation data available with you at that particular location, this location for the last 100 years. And typically, you also use all the climate predictor variables, for example, mean sea level pressure and geopotential height, at all these locations from the NCEP reanalysis data, which are available from the same period as the historical data. And then develop a statistical relationship between these two, hold the statistical relationship intact, go to the global climate models, and look at how they are predicting these two variables. And because once you know these two variables, you can put that into your statistical relationship and generate precipitation. That is how you do this. This is slightly old one, and we use the EAR, the third assessment report of IISc. As you change your models and the scenarios, you will get a different prediction order. This is from 2001. Many of them may not even agree on the sign. Some models might say it is likely to increase, something may say it is likely to decrease. So there is a large amount of uncertainty associated with the projections that we make using the global climate models. And we need to address these uncertainties associated with it, for which we develop several models. Even the statistical models, there are many ways of doing it, and very rigorous ways have been developed in our institute. So these are some of the ways by which. But then you address the uncertainties. One is assume that all the model scenario combinations are all equally likely. Because of our ignorance, we don't know how the future is likely to unfold. Therefore, we are ignorant about the future. Therefore, whatever the model scenario combinations that you have, assume that everything is equally likely. You don't know anything about it. Therefore, we fall back on any of these model scenario. The second one is you look at the immediate one. Let's say between 1990 to present, last about 20 years. How these model scenario combinations work during the last 20 years, and then assign weights to these time series that you generate based on how well they have performed. The third part is not only look at the historical period, but also look at how well they are together as we use them into the future. So how well they are together into the future. So all these three different levels of uncertainty we address, and instead of providing one particular time series as a projected hydrological scenario, we provide probability distributions. That means we say that the probability distributions of, let's say, precipitation at a particular location is likely to change in the future like this. We use the basin methods and then assign probability to weights and so on. When you look at how well they are together into the future, you see that as time progresses, one of the models in this particular case starts falling apart. This is the GIS's model. For monsoon, it is notorious. GIS's model always falls apart. And then you assign weights associated with that. How well they have performed. There are very good and rigorous sophisticated methods of assigning these. It's called as the reliability and reliability method, because you have an ensemble of time series. There are ways of analyzing the time series and and then you provide one weighted CDF, cumulative distribution function, for different time intervals, 2020 to 2040, 2040. Now these will be useful in planning for water resources. Then we look at the stream flows. What we did with the precipitation, we also do with the stream flows. Except that for the stream flow, you remember we can use the hydrologic models. You projected the precipitation at that location. Similarly, in a particular basin, you would project precipitation at various locations because there is a very large spatial variation associated with the precipitation. You generate precipitation into the future at various locations. Use your hydrologic model and generate stream flow at that point with all your other study centers. That's one way of it. The second way is, anyway you are using relationships between the climate variables and the hydrologic variables, you directly use the stream flow, so that you are doing away with all these middle variables. Directly use the observed stream flows and the historical data and the predictors, develop relationships between the climate variables and the stream flow directly, and use them as predictors for the future. Now in this case, we use surface temperature, geopotential height, specific humidity, MSMP, etc. There are ways of filtering out these predictors. You can simply do some correlation analysis, take a large number of variables which you suspect are affecting that particular variable, and then filter them out, come out with only 3 or 4 variables. Even when you have 3 or 4 variables, for the grid size that you have and for the time series that you will have, the size becomes very large. Let's say you are talking about 16 grid size. Around that part. At every grid, you have 4 variables. So 16 into 4, 64 variables. And then you have a time series associated with it. Let's say 100 years of time series. So the size of the problem becomes large. We do the principal component analysis to bring down the size. If you are using, let's say, multiple linear regression or neural networks or any of this regression type of things, and bring down the size and simulate the flows. And provide what are called as the flow duration curves. The flow duration curves are the single most important design parameters for all the hydrology. Typically, it shows, for example, at 70th percentile, what is the flow that is equal or exceeded. And this is the historical flow, and how different models predict the flow duration curves. You imagine the middle level flows, which are around 60%, 50%, etc. If these are reducing, that will directly affect your water availability for your hydropower generation, irrigation, domestic water supply, and so on. So it is important for us to assess how the flow duration curves are likely to change in the future, and that is what we do. The next application that we are talking about is on urban flooding. You know now most of the cities regularly get flooded during the summer period. The first aspect is that the land use is totally messed up in most of the cities. That's definitely there. But there is also something happening that one. The intensities of short duration rainfall, they are increasing. And these two together are causing extensive problems of urban flooding in the cities. So we need to ask the question in the phase of urban climate change. You just look at the hydrographs. Hydrograph is simply distance versus time. If you look at the hydrograph generated by precipitation here in this catchment, which is completely developed, what happens is the flow quickly takes off, and then it reaches the peak very fast. And then as the rainfall stops, it also quickly comes down. Whereas in this type of catchment, this is pre-urbanization. It picks up very sluggishly. The peak is much smaller, the peak occurs much later, and because of which there is a problem with the urban runoff. In the urbanization, the hydrograph has a higher peak, has a faster peak, and the total runoff is larger. compared to a non-runoff. And the question that we need to ask is, how do the short-term intensities of rainfall respond to climate change? If you are, I'm sure you are all of you are from one city or other, you have seen that if the rainfall occurs for around 2 hours, 3 hours, the entire city is flooded. And within these 3 hours, what has really caused the flood is that critical 15 to 20 minute rainfall. Because, like we pointed out, the time of concentration is very, very short in the urban floods. The rainfall occurs and quickly it comes into runoff. And therefore, the time of concentration is very short, and hence it becomes critical. Therefore, we have to look at short duration rainfalls, high intensity short duration rainfalls. And at the Bangalore, for Bangalore city rainfall, we have just looked at the historical data. As you can see, for a given duration, the intensities are continuously increasing. Just look at the historical data, don't even look at the future. The intensities are continuously increasing for this. Then we look at the climate models, do all of this analysis that I mentioned, but we have to look at short duration periods now, typically of the order of 15 minutes, 30 minutes, etc. And the climate models are notorious not to perform well for short durations. So what we do is, we use the simulations available at 1 day duration, bring down to shorter duration. So apart from bringing down on the spatial scales, we also bring it down on the time scales by using stochastic disaggregation techniques. And then see for given durations how the intensities are likely to change. Remember, as I said, because the time of concentrations are very small, we need to look at intensities of the order of, for durations of the order of 30 minutes and so on. And there we see that for Bangalore city, these are continuously increasing for a particular class. The final part is what happens to the agricultural demands. You must know that about 80% of the water in this country is used for agriculture. So unless we manage the agricultural water correctly, we won't be able to separate the water resources aspect correctly. So we need to first look at how the agricultural demands are likely to change for the same given cropping pattern. We do not manipulate the cropping pattern, but the climate is changing, therefore how the agricultural demand will change. Like I said at the beginning of the class, the evapotranspiration will dictate how much water is needed for the crops. And therefore, the change in evapotranspiration because of all these variables changing, temperature, radiation, relative humidity, etc. All of these we need to study with respect to evapotranspiration. So what we do is, we pick up all the variables, rainfall, downscaling to that scale, similarly relative humidity, wind speed, downscaling, bring it down to that scale, maximum and minimum temperatures, downscale and bring it to that scale, and then calculate the evapotranspiration. We have seen the evapotranspiration model earlier. We put all of these as inputs. We started with the global climate models, used the downscaling model, we used some predictors for that, and bring it down to the hydrologic scales and relate it with evapotranspiration. This evapotranspiration we convert it into water demands. And see that for the same given cropping patterns, as the climate changes, the water demands will start increasing. So on one side, you are seeing the flows or the water availability is likely to go down. I keep using the word likely because there is uncertainty associated with it, and then we only talk in terms of the probabilistic projections. And on the other side, the water demands are likely to go. And therefore, the situation with respect to water is likely to become critical, and we need to develop what we call as adaptive responses to such a mismatch. Thank you for your attention. We have 2 minutes for questions. Thank you.
Yeah. For the hilly areas, the statistical transferring will be better or statistical?
See, for the hilly areas, first of all, the data will be very small. If you are looking at the MRN, there are no gauges available. So the data is very, very sparse. The second part is if you are looking at the western part, there may be data available, but the predictors that you use must be carefully chosen because there is an orographic effect and so on. So you need to look at the predictors correctly for that. So perhaps you may have to use a combination of statistical as well as physical methods. And statistical and stochastic are more or less similar. In the stochastic disaggregation method, all we do is conditional probability that we use. In the statistical, we use regression type of transfer function type of. But you may need to bring in some physical features into the Western Ghats. Western Ghats type of missions. And for the Himalayan regions, the problem is that we simply do not have adequate data, and therefore we may have to do several proxy data for that and use several proxy data and then estimate.
So, general questions regarding the modeling. What should be the ideal length of data set for the calibration period?
Yeah, this is always a problem in our country because for hydrology you don't have much data. But for a meaningful assessment, at least 3 decades of data is necessary, 30 years of data. So what probably you can do is, in the Upper Ganga basin that I showed, we have done that you divide it into 3 sub-regions because the land surface is changing very drastically. And first, let's say second region and third region are similar. And for second region, you have enough data to calibrate. You calibrate with respect to that and use that calibrated model for the third region with whatever is the data that you have. In our case, we had only 6 years data for the other. But you then have to check and make sure that hydrologically these are similar. But for a good calibration and validation model, you need about 30 years. 3 decades is work. Okay, thank you.
Okay, so